Hello, everyone. This is Yu Song, and today we are going to talk about the chapter two activation functions in our book on deep learning architecture, a mathematical approach. So, as you may all know, that activation functions is a really important things that every neuron or every basic element of the neural network will use it when doing the calculation and finish its job. So, in today's video, we will follow the book to explore more things about what activation functions and what this family of functions contains and how they can function with the neural network. What's their characteristic? So let's begin, right? Uh, Today's video, basically, I divided into three main parts. First of all, introduction. Second, the sigmoid function and the scratching function. Actually, the introduction and the sigmoid function are the main body of our video that they contains the majority of the things. So in the introduction, we will basically introduce you tons of the member of the family of activation function from linear step hockey stick to sigmoid bump type function to and even we are going to briefly introduce what are memory theory from analysis and talk you something more with the sigmoidal function and more general scratching function. So let's begin. So first of all, the introduction. Let's see. So in a neural network, each unit of the network will use a function to process the income signal, and the function we use is called the activation functions. And the importance of activation function is just to introduce a non-linearity into the network so that non-linear approximation of the target function can be learned. Because like in our last video, we had already seen if we do the linear regression, using a full linear activation function, which means y equals to cx, that is just exactly the same process you do when calculating the linear regression. That means, in that sense, neural network can only handle the problem or classification problem linearly. So those linear problem are the only thing we can handle with linear activation function. However, that is definitely not what we want in fact, because many things, or say most things in our real life is non-linear. Okay, so that's why we need some more activation functions. And there are some main types of activation functions used more often. Of course, you can use any kind of function as that activation function, as long as they got some specific characteristic to help you finish your job. But still, there are lots of things being mainly studied by many mathematicians and computer scientists. So first of all is linear. The second one is what we call step. And the third one is sigmoid. And then the fourth one is actually what we say called hockey stick type function. So those are things. So let's begin one by one. First of all, the linear function. The linear function is actually the simplest activation functions. I'll say f equals to kx as long as k is greater than 0. Why k is greater than 0? Frankly, I don't know, but there's no linear activation function with k smaller than 0. And we know the identity function in this group is actually when k equals to 1, that is when fx equals to x, that is identity, really straightforward. And as what we have seen in chapter 1, that computing with a neuron with a linear activation function is equivalent to just a linear regression. So there's nothing fancy about it. We don't want to stay too long at this part in this video. So let's look at the second type of activation function, the step function. Actually, this type of function is really amazing. It is a biological inspired. There are two examples, as you can see. But why I say it is biological inspired, it is just like if I have a pen here and I get out the pin of the pen and I stick it I try to stick it into my skin. Don't try this at home yourself, right? You will not feel hurt until the hurt level reach to some threshold before you can feel like, okay, it is a little bit tough or it is a little bit pain. So that is what I say biological inspired, and that is exactly how your neuron in the brain works when there are some chemicals when you receive, for example, you receive the signal for pain, you have to accumulate enough chemical things between chemical. I don't know. I'm not a chemist, but I think you have to accumulate enough chemicals between neurons so that the next neuron can feel okay. It is what the former neuron tells me. So that is what I mean by saying biological inspired. And as you can see in the screen, there are two examples, and there is not significant difference between them. One is from 0 to 1, and the other one is from -1 to 1. So the left side function is called Heaviside function, and the right side is called signum. But actually, in the later we will give them another. I will give them. I will call them in other names because the name a little bit hard for me to remember. So let's see what exactly are their expressions. First of all, the stereo step function, as I said, stereo. This function is also known as binary step function and unit step function. So a heavy side function. So this function is given by hx equals to 0 if x is smaller than 0, and 1 if x is greater or equal to 0. So, and the image looks like this. Note that at point 0, x equals to 0 is non-differentiable. It's non-differentiable. It's not continuous at that point. So the other one is what we call the bipolar step function. This function is also known as the signum function, given by Sx equals to -1 if x is smaller than 0, excuse me, and 1 if x is greater or equal to 0. So that is the expression. And as before, this is the image, really straightforward things. Still, it is not differentiable at point 0, and it is not continuous at that point. Do they have any kind of relationship? Yes. Hx is this one, and Sx is this one. And we can see that the Sx equals to 2hx minus 1, and its derivative is excuse me, s prime x equals to 2h prime x equals to 2. This one is the Dirac function x. So this one is known as the Dirac function, which will help us to get over the problem that these two functions is not differentiable at x equals to 0 by Schwarz distribution theory. But that is not the main target of today. That is not what we want to discuss with activation functions. So if you're interested in that, you can go look why we can get over that from a perspective of a general function instead of the specific function analysis perspective. All right. So let's look at another type of function. Is what we call hockey stick functions. This class of function looks like an increasing L shape. Actually, this is a word from the book. It not look like an L because it's not increasing this way, but it's like a reverse L, increasing the other way. But anyway, this is the first thing we can see. Rectified linear unit, also known as ReLU. That is how I pronounce it. You can call it ReLU. English is too complicated. And given by ReLU equals to x times hx. Remember what is hx? The base step, the shell step function, or right, unit step function. Or Heaviside function, if you like, and it equals max x0, or in a more easy way to see that it equals to 0 if x is smaller than 0, and it equals to x if x is greater or equal to 0. So it's This image just look like this. Stay 0 until x is getting larger than 0 and have slope 1 increasing after 0. So that is what we know for ReLU, really famous function. Remember that it is really useful, especially in the hot field these days, like computer vision field and NLP. It got some more complicated use these days than days before. So another thing is what we call the p-ReLU, parametric rectified linear unit function. So it's a piecewise linear activation functions that p-ReLU. We got a parameter here, alpha, and it equals to alpha x if x is smaller than 0. Of course, alpha need to be greater than 0, and x equals to x if the x is greater than 0. So, and the other thing, exponential linear unit, don't excuse me if I'm going too fast, but for this part, we do not have too many things to talk about. They are just functions, and it got some, each different functions got different usage in different case, which is something I cannot tell just through the pure theory. So from a theory perspective, they are just functions. There's nothing fancy about them. So this one is what we call ELU, right? ELU alpha x equals to x if x is greater than 0, and alpha e to the x minus 1 if x is smaller than 0, is smaller equal to 0. And you need to see that it is differentiable at x equal to 0 if alpha equals to 1, and only when alpha equals to 1 it is differentiable at that point. Otherwise, I'm not sure. I don't think you can testify it out yourself. It's not hard. And another thing is what we call scaled exponential linear unit of CLU. So CLU, we introduced another parameter here just to time it by lambda times ELU, and then we got CLU. So right, it makes sense actually. Another thing is sigmoid linear unit. I made something more here because it is special. Let's look at this phi x equals to x times sigmoid x, and this sigma x. This sigma x is what we are going to talk about later, is what we call the logistic sigmoid function. And this sigma x, then we have phi x equals to x over 1 plus e to the power of negative x. And the special things comes here, that this activation function is not monotonic, which means it's not always increasing or always decreasing. But its derivative shows this, and also you can see there is a critical point of the function that makes the function value to be the smallest through the whole range. So that's the sigmoid linear unit function, and its critical point is that x0 x0 approximately equals to minus negative 1.27. You can solve it by solving. Okay, this is the sigma x equals to 1 over x. You can solve that. Okay, that is CES rule, and the local point of the critical point, and the value can be adjusted with another parameter given say c, that phi cx equals to x sigma cx, which I apologize, this part of negative cx should all be to the power of e altogether. And here the image get a little bit big. That's the weird point of LaTeX. I apologize, but as you can see, if you apply different c here, of course the critical point is different. Also, you can see if here you saw if here you saw this one, the sigmoid cx equals to x over 1, of course the result will be different from c to c. All right, let's see another thing is what we call soft plus, or short as SP. So SPX equals to ln 1 plus e to the power of x. It is also straightforward, has a image from 0 to infinity, and fx equals to, what you should note here is like it got some special relationship that the SP x minus SP negative x is just equals to x, and the prime of it is exactly, right? You are familiar with this, right? And the inverse of this function is log e to the x minus 1. Sometimes this one is also useful, but that is what we have for hockey stick. That is a hockey stick function that looks like an L, remember that? Another thing here, we are going to talk about sigmoid. This type of activation functions got a really strong advantage because they are smooth and they can approximate a step function to any degree of accuracy. And their range, sometimes its range will be from 0 to 1. And in that sense, its value can be interpreted as probability. That's why lots of research you can see use the sigmoid function because just because that probability benefit to interpret it so that the researcher do not need to reshape its output to the range between 0 and 1, which is a big advantage for of sigmoid. Okay, so first of all, the logistic function with parameter c greater than 0 is defined by this one. So it is just a sigmoid cx equals to this one equals to 1 over 1 plus e to the negative cx. And its function, its image is here, as you can see. We apply some different c here, and you can get some different value here. And you can see, actually, I'm sure that this one is got a bigger c, so you can see it actually approximated the step function. It really looks like, and if you keep increasing c, you will have a really good approximation of the step function. So that is what we said about the logistic function in the former slides. And the sigmoid function, sigmoid function approximates the binary step function or Heaviside function hx as c approach to infinity. We can see from here that the limit c to the infinity, this one equals to 0 if x is greater than 0, and infinity if x is smaller than 0, which will lead to you this kind of things when you can just apply it, calculate the most basic calculus 2 or 3 knowledge, and you will get, okay, its limit is just the Heaviside of its binary step function. All right. So the logistic function will map the entire real line monotonically into the unit interval between 0 and 1. That is something really good, really amazing. And so it, besides those advantages, it also satisfies certain differential equations, which we will discuss later as we reach to the minimum searching algorithm, or even or the back propagation. Sorry about my language, God. Algorithm. So its derivative. Let's calculate its derivative, and you can use the coordinates rules as that is also, I think, calculus 2 level knowledge, and you can get the derivative of it is actually equals to c times the sigmoid function times 1 minus the sigmoid function, sigmoid x, and thus, okay, you got its derivative equals to c times sigmoid function times 1 minus sigmoid function, right? That is its derivative. And if c equals to 1, for the derivative, we will talk about it later as we found something more fancy, right? If c equals to 1, we obtain the standard logistic function, which we will use in the future to construct a sigmoid neuron, and that is the sigmoid sigma x equals to 1 over 1 plus e to the negative x, which is the most famous thing, as famous as ReLU these days in the deep learning field. And obviously, we can see that okay, sigma c minus x equals to 1 minus sigma x, and a more generalized we can generalize it into two parameter sigmoid function by just adding another alpha to it, and this function, this generalized sigmoid function, will be more useful when we consider a neural network as a universal approximator of the functions. So we will keep it here. You can just know that, okay, there are different kinds of sigmoid function, different logistic parameter, with one parameter, with two parameter, and a standard logistic function. That is definitely enough for now. All right. So sometimes the inverse of sigmoid function will also be useful. We call it a logit function, and it's being given by, okay, sigma negative 1x equals to log x over 1 minus x, and that is sometimes it will be useful, but for now we tend to just skip it. I also note that the SP function we talked before, soft plus function, can be recovered from the logistic function, as I mentioned before. Okay, so it is SP equals to the integral from negative infinity to x. So that is okay. Another sigmoid-like function, we call it hyperbolic tangent. Hyperbolic tangent is somehow many of you has been really familiar with. So sometimes we call this function bipolar sigmoidal function, and it maps the real number lines of the things in real field into the interval from -1 to 1, and having horizontal asymptotes at y equals to positive and -1. And the function is defined as this, just the tangent, hyperbolic tangent function. All right, we shall notice that by some algebraic computation, we shall see that Tx equals to 2 times sigma 2 x minus 1, which is the relationship, which is the relationship between the hyperbolic tangent and the standard logistic sigmoid function, and its derivative is given by t prime x equals to 1 minus t square x, right? Think about it. Is it really familiar to you? Yes, the well-known differential equation. It's something we definitely want to show, definitely want to see, and remember that its derivative is just that famous differential equation, which is amazing. And this will be really useful in the future when we talk about the back propagation algorithm that is always useful in these days in the neural network field. So keep it in mind for now, and we will use it later. At that moment, I'm not sure whether I will refer back to this video or not. So here is the arctangent function hx. Arctangent function. So it is the hx from the real number to 0 and 1, and hx equals to this equation. So another thing is soft sine function, also known as Hans function. It's another increasing sigmoid function from r to -1 to 1, and it's given by this one SO, x equals to x over 1 plus x, the absolute value of x. So it has been shown some advantage of using soft sine over hyperbolic tangent. In fact, that it saturates slower than the hyperbolic tangent. As we, you can try to draw out the image of these two functions, and you can obviously see that in some it saturates slower than hyperbolic tangent, but I'm not able to tell you in which case it will be more useful. That is something really hard for the theory to tell you, and that is well, one hard thing, one difficulty of learning neural network is without the real case, you can hardly understand what is the engineering side or computer science side of the neural network. But here we want to focus on the mathematics. So some piecewise linear function. This one is piecewise linear function given by this. It's okay, and its function is given by this. Note that it is -1 and 1, and some place during this part is x over alpha, and that is it is piecewise linear, as you can see. So those are some sigmoid functions. Furthermore, that even though these kind of functions are not normally used, we still want to introduce them. The first one is the Gaussian function, which is also the Gaussian distribution. It looks like a Gaussian distribution. So it is the bump type function, which is like the bump of your heart. And the Gaussian is given by this. Double exponential function is given by this. These are their image. The left side is Gaussian, and the right side is the double exponential. So there's nothing too complicated about them. If we are going to use them in the future, we will refer back to them. But for now, just know that okay, this kind of function can be also used as as activation functions. So don't quit my video saying okay, there are only three activation functions in neural network. One is ReLU, the other one is step, and the third one is sigmoid. And that's enough. You should know that there are some other kind of activation functions that is useful in some specific cases. Okay, and another thing is the classification functions that is somehow interesting. So actually there are multiple ways for you to represent the information, and one way is what we call one-hot vector, using one-hot vector, or say one-hot representation method, or say one-hot encoding method. So one-hot vector is a vector with n component in the n-dimensional real space of the form ei equals to 0, 0, 0, 0, and 1 space 1, and 0, 0, 0, 0 for the rest, with A1 on the S entries and 0 in the rest, which is super useful in classification problems. All right. So if one would like to have the network output as close as possible to this type of function, to this type of representation method, then the activation function of the layer should be the softmax function. Sorry, one of the light there dies just. And if x is in n dimension is a vector, define the n valued function softmax y equals to softmax y equals to z by this one z, and so here equals to e to the power of xj, and here is the norm of e to the x. Here we use the norm, we use the L1 norm here, but actually other type of norm can be also used as well. So okay, here is what continues, that we can also define the softmax function depending on one parameter c greater than 0 by doing this. And actually the Euro softmax function is when c equals to 0, and but if c equals to goes towards to infinity, we can obtain that it equals to 0, 0 equals to ek, and ek is the biggest element of the entries. So we can verify this when n equals to 2. You can also do it with n equals to 3, n equals to 4, as long as you want to calculate. So limit we have limit c to the infinity softmax this one. We first assume that here we have entries to x1 and x2, and the so that the softmax function will be like this. And as c goes to infinity, you can simplify this a little bit, and you will get 1, 0, which is tells you the location of E1. That is really amazing, right? Yeah, you can just use some simple calculation to tell, okay, which one is the biggest uh, in the entries. That is fantastic, right? All right, next, for now. Sorry for the rush, but we had already seen most of the activation functions that you will use from time to time. And the next one, before we head into the sigmoidal functions, before we talk about some more general questions, I want to talk to you a little bit with the measure theory on the sigma algebra. So sigma algebra, what is a sigma algebra? Sigma algebra is an algebra, of course. So what is a sigma algebra structure? Like, let's E be a finite site, and AI is the subset of E, or in E. So we have a algebra structure. We call it epsilon here. Actually, this is capital E, but I call it epsilon. And if epsilon meets the following property, is called sigma algebra on E. So what does that mean? The two properties are, first of all, it can be union. It can be infinite. It can be finitely union. And the second thing is this one, the complement of any site in that site is also in this algebra structure. So these are the most basic sigma algebra structure. And if you apply De Morgan's law, you can also see, okay, as long as you have finite intersection, the intersection shall also be the algebra structure, and that is enough. Then next, what is the Borel sigma algebra? The Borel sigma algebra BR is the sigma algebra generated by all the following collections that, okay, from infinity to x open, from negative infinity to x closed, x to y open, x to y closed, and x to infinity. Of course, I want to talk more about sigma algebra, but as I said, sigma algebra is not our main topic today. So we will briefly skip those algebra terminology a little bit and talk about the main result we are going to use in the future. So, and if in the future, for example, in the chapter like 9 or 10, if we need to use sigma algebra and refer back to it, we will give more things on measure theory. So then we talked a lot about measure theory. What is a measure? So actually a measure is really simple. It is just a way to access a body of information. So this can be done using a mapping, using a function from this mapping mu from that epsilon to the positive of real number and union with infinity with the following properties. So first of all, if you have an empty side, the mapping equals to 0. And if for the union of an, for the union of an, actually this an should be outside, a bigger an. For the outside, for the union mapping of that union, it should equal to the sum of the mapping on each side. So as long as those side union are disjoint from each other, so that is what we call the countable additivity. All right. So, and the triplet E, which is the finite site, the epsilon is the algebra structure on that finite site E, and the mu, which is the mapping, is what we called the measurable space. Is what we call a measurable space. And so if we have here E epsilon, that is, I need another barricade, my apologies, and IFF are two measurable space, a function f is called measurable. Sorry, a function f is called measurable if the inverse of that function is of b is in epsilon for all for all b in f, or say in another way that the inverse of f from E to F, the inverse of it is part of the epsilon. All right. Okay, let's look at some measure as just what we did to the activation functions. First of all, the Dirac measure, let x be a fixed point, and the for all a in that epsilon, we will have this one. If it's in, then the function value is 1. If it's not in, the function value is 0. Right? It is a measure on epsilon. And another function, another measure is what we call the counting measure. So if D is a subset, if it's a subset of E, be fixed and finite, define this one by this one we call the card. I don't know what's that mean. Card A intersect D equals to this one here. The measure, the mu is a measure on epsilon, and it counts actually the number of elements of A that is in D. So those are two measures, which is not that always referred to when we discuss when we have a discussion in neural network field. So we skip them quickly, and this one is also not always widely used. We call desecrated measure. So let D be part of E, be fixed under desecrated. Define Mx be the mass of X, and Mx is greater than 0. So for X, if X is in D, and consider that mu A equals to the mass of A, which equals to this one, and for all A that is in the epsilon, and then the mu is a measure on epsilon, which means U, the mass of A, and that is a little bit abstract, but there's not a lot of good ways to understand them. The next one, Lapska measure. This one is famous and useful. This one is famous and useful. So you can consider that E is all the real number, and the sigma algebra epsilon structure is this one, is what we call the BR, and mu is defined for any open interval as their length. For example, if mu AB then equals to B minus A, which is the distance between B and A. And if you extend mu to this Borel sigma algebra, it is to this sigma algebra structure, it is called the Lapska measure on the real number. All right. The next one is Borel measure. Borel measure is what we will talk the most oftenly in the neural network field. Also, there are so we will try to focus on this and light the BR to the power of n, which is BRN, be the sigma algebra generated by all the open side of Rn. A Borel measure is a measure that from BRN to R, when n equals to 1, mu is a Borel measure on the real line. So BR to R is a measure on real line. R2 to R, you can think of it, okay? Right, on the plane to the real line, and BR3 is a cube to the real line, right? It's straightforward a little bit. And if mu is a finite measure, we can associate it to the function fx equals to mu from negative infinity to x closed, which is called cumulative distribution function. And this function is monotonic increasing and also satisfying this kind of relationship that mu A B equals to fb minus fa. So for instance, we should remember that the Lipscomb measure is a Borel measure. If we are really interested in that, how to say the measure theory is something that you will study maybe for 1 year in your grad school. So for now, we can just have those kind of things in mind. It's not really necessary for you to understand that. And as before, if in the future we will use some more detailed knowledge, I will add them at there. All right. Some property of the measure. If this is a measure space and the following properties will hold, first of all, it's finite additivity. If something intersect equals to empty set, which means they are adjoints, that means mu, the measure A plus B equals to measure A plus measure B. All right, and so you can expand that to finite, countably infinite, finite additivity, right? And monotonically, monotonicity. So yeah, if A is a subset of B, that indicates the measure of A is smaller or equal to the measure of B for all AB is in the epsilon. And the other one is sequential continuity. And the fourth one is a Boole's, the Boole's, I can't pronounce the name correct, inequality, which means the union of an of n, the measure of that is smaller than the sum of measure on each of them. As you can see clearly that because maybe I think it is being proved by some of them got the intersection of each other, so they cannot be fully adjoined with each other. I think that is how it's proved. But if I'm wrong, yeah, I don't know this part too well. All right. The next thing, I've already told the next thing, the integration in measure. So this is a measure space, and f is from the finite side to real, to the real line, and be a measurable function. Then the objective, this one, the mu f equals to the integral of e fx mu dx equals to integral e f d mu, represent an evaluation of f through the system of beliefs in mu, and is called the integral of f with respect to the measure mu. All right, that's it. And this is defined by the following steps. As you can see, you can pause here a little bit to look at the process. And here is the sigmoid function, If mu f is smaller than infinity, then the measure function f is called integrable, and the non-negativity, linearity, and monotonicity property of the integral are given by this. That is, mu f is always greater or equal to 0. The mu af plus bg equals to a mu f plus b mu g for ab in a real number, and if f and g are all measurable, and still, as what we can see before, if f and g, if f is smaller than g, smaller or equal to g, the mu f is also smaller or equal to mu g. So that is something we can see, and you can try to prove on your own. We will skip the proof there. Okay, the Lipscomb integral, that is the last thing we want to discuss in this subsection. The Lipscomb integral, that is e equals to the real number, and right, the epsilon is a Borel algebra, sigma algebra structure on the real number, and let mu be the Lipscomb measure on real space. So in this case, that mu f will equal to this one, is what we call an Lipscomb integral of f on e, and the integral of f over set a in epsilon is defined by this one, that the integral a f d mu equals to integral e of the identity thing in A times the U, which is just the mu of F times the identity thing 1A, and in particular you have here okay, it is not too hard still. You just need to keep them in mind a little bit, have an image of it, or it's good enough already for now. We will use them, we will revisit them from time to time in the later. So don't worry if those kind of things are too frustrating for now. And okay, the next part, sigmoid functions. Sigmoid function, what are sigmoid functions? So basically the sigmoid function is something, the rough idea can be generated by looking at the image of all the sigmoid function. We mentioned before, if you look at their image, you can always see, okay, they always show some kind of trend, like going flat at first and increase and going flat again. This kind of relationship, just like what in the hockey stick function side, you can call it, okay, L shape, increasing L shape function. All right, so this function, if something is called sigmoidal, if its limit to infinity is 0 and its limit to the sorry, this part should be negative infinity. I mistyped. This is another typo. Next time you can try to count how many typos I made in those slides. And here is the if x goes to infinity, the sigmoidal function should equals to 1. And that is the definition of sigmoidal function. And recall that a measure mu can be regarded as a system of beliefs used to access information. So that the mu x equals to mu dx will represent an evaluation of the information case from the information case to x, and thus the integral will represent the evaluation of the function fx under the system of belief mu. That is what we said in last subsection. And next thing we want to introduce you on a terminology called a discriminatory function. So the definition of a discriminatory functions is this: if mu is a Borel measure on In, and a function sigmoid, a function sigma is called the discriminatory for the measure mu if it meets this requirement. If this one, then it indicates mu. If this one is true, then it indicates that mu equals to 0. And here In equals to just the unit of different dimension. In equals to 0 to 1 times 0 to 1. If it's n equals to 1, that is the line segment from 0 to 1. If it's 2, that is a unit square. If it's 3, that is a unit cube, right? And M represents the Borel measure. Oh, my bad. This measure we didn't talk in the last section. I will try to make another video to fix this up. And note that you can see that I made a language mistake just before when I read this one. That this one is not the sigmoid function. It does not have to be the sigmoid function. As long as it meets this requirement, it is fine. This one is just the sigma symbol. All right. So let me talk two really interesting things. One is called the hyperplane, and the other one is called open half spaces. I don't know typically where this kind of terminology will be introduced in mathematics, but I first learned those two things in the convex optimization. So it's a little bit strange, but the hyperplane is just this plane defined by this, and normal vector is just W, and the n plus 1 intercept theta is given by this, and this hyperplane, you can just think it as a plane. Is this just a node? This plane does not have to be in the three-dimensional space, and you can consider two open half space. one is on the one side of the plane, and the other one is on the other side of the plane. As you can see, as you can see here by their expression, it's just like there is a plane in the three-dimensional phase, and this is in three-dimensional. This is a hyperplane. This envelope is the hyperplane, and on the one hand it is a half space, and on the other side it is another half space, right? Just to consider the xy plane in the three-dimensional coordinates, and you can see the relationship that this n-dimensional space is being divided by the hyperplane and one half space and the other half space. So if you union them together, you will get the whole space, and that's it. Here's one lemma. The lemma will tell you whether mu is equals to 0, and from there it will help you to better identify whether something is what we call the discriminatory discriminatory function. So here's a lemma. I will pause here for a little bit while for you to pause and see it, because we do not want to give any further proof here. If you are interested in, you can definitely contact me and I will make another video. But for now, I think it is not, it is better not to go too deep into those kind of things for the first time readers. And that is also the recommendation of the book. So here's another lemma, that any continuous or bounded, I'll say bounded measurable sigmoidal function is a discriminatory for all measure that is on MIN. Also, in the book, it says like it gives a long proof about 2 pages, and it says like any continuous sigmoidal function can be replaced by bounded measurable functions because some properties of which kind of functions are measurable. But for the same reason and from the same recommendations of the book, I tended to not put you a 2-page long proof here for the first time. All right, but I promise you in the future, as we talk more and more about the theory sides of the neural network, about the information processing through that process, we will give you tons and tons proof. So those are sigmoidal functions. And then the next one, we want to briefly talk about the squashing function. And the squashing function is actually just a definition. A function is called the squashing function if the function is from R, the real line, to it maps the real line to the interval 0 and 1, if it's non-decreasing, and if the limit of this one as it goes to negative infinity is 0, and as long as it goes to the positive infinity, it reaches 1. So squashing functions are measurable with respect to the Euro-Borel sigma algebra, and the reason why here we want to stress the squashing function is that is because it is more general, and when we deal with the Borel site, that this kind of function got some more advantages over the functions we specifically mentioned before. You can try to testify like the activation functions we mentioned before, which of them are squashing, which of them are sigmoidal. That is things leave up to you. But just by verifying the definition, it should be really straightforward for all of you. And all right, here, let's do some summary. I know it is a really long and maybe boring video, but thanks for you to stick and you here. As we mentioned at the beginning of this video, the activation function is just to introduce a nonlinearity into the network so that the neural network can communicate, can done much more complicated works than the linear regression if we just use the linear activation functions. And actually knowing so many activation functions is really frustrating, right? Just think back in your mind. Can you remember what is ReLU, pReLU, CLU, SLU, ELU, what's their expression, right? It's really hard. But still, we can keep and bring away some things. The first of all is that these days, as we have more development in the CV side, which is the computer vision, we tend to see more advantage of the ReLU function than before, and it seems to be performed better in image-related job, not only in the image recognizing the computer vision, but also in the like text to image, this kind of job to understand people say and generate image, like GAN system. It got some wide use in this kind of field because on the one side, because it's do not saturate, and on the other side, it has some other advantages that we will discuss in the future if we got a chance to talk about more detailed things in more specific jobs in the image-related job. All right. The next thing is that logistic sigmoid function shows its capabilities for already for like decades in handling multiple multi-layers neural networks, even though it's because it's derivative, because it saturates. There are some problems with it. We will deal with in the future, especially at the place of backpropagation part. But for now, you need to know, okay, the logistic sigmoid function, even though it looks hard, but it actually got good capability on handling the multi-layer neural networks. And the third thing is hyperbolic tangent shows a trend on performing better than the logistic sigmoid function in specific case. Okay, as you can see, I mentioned so many times specific cases. In today's video, that is something I cannot avoid, that is a little bit inevitable, because just by talking about theory, I cannot tell you in which case it should be used, because the analysis of the computer science, the process of neural network processing is really hard, and it got still lots of things left to be studied. So those are the things I cannot tell you. You have to get hands on some actual neural network research or neural network project to see, okay, which one will works better in the model training part. And that is something really hard. Also, okay, that is something you should bring away. As always, I will put my contact information at the very last. And if you have got any ideas, any interest, any thoughts you want to share or you want to talk about, you can definitely shoot me an email if you found something is wrong. I talked something improperly or express a wrong idea. You can always I always appreciate you to send me an email and tell me about those kind of things. All right, that's what we have done today. For next chapter, we will talk about more things on the objective function, on the cost function, which is our goal of neural network, of what we are going to study. That is also amazing, and I hope to see you in the next video. Thank you so much.